Here we're going to take a look at the commonly taught significant figures rules that are learned in high school and general chemistry classes that you pretty much see in textbooks. Is this a completely comprehensive understanding of significant figures? Absolutely not, but it's good enough for the level that we are going to be approaching. I will point out a few things as we go along in our next couple of videos about significant figures, about some commonly misunderstood things about significant figures that some textbooks unfortunately don't really address, but I will try to address for you, at least to the degree that you need to know for this class. So, significant figures, once again, as in our previous video, are ways of reporting numbers and representing values and interpreting values in scientific measurement that reflect, in a sense, an honesty in reporting and trying to really get an idea of what is considered accurate, realistic measurement. So how these rules play into that, we'll be getting further into as we move along in this section of videos. I don't want to try to lay too much on in, a 6-minute video, but so let's go ahead and get at the most basic level here. So rule number 1 is that all non-zeros in a number are considered significant. So that's the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are inherently significant in a number. If you have zeros between non-zeros, they are significant. And that a zero is significant if it is a reported part of a reported value that is after a decimal place. We're making the assumption that that is a number that really reflects a level of accuracy in a scale or graduated cylinder or whatever that is being actually measured, or maybe a clock that measures into fractions of a second. However, zeros at the end of a number that are not explicitly after a decimal place generally are not considered significant. And leading zeros, and I just misspelled leading, that was a little silly there, L-E-A-D-I-N-G, leading zeros are not significant. So why are these numbers not significant? It really is our next video that will explain why, but let's go ahead and just apply it as is to 6 example numbers that we have right now. So we have the numbers, that should be 6 million, making a lot of errors today, 6 million, and then a fractional value, 0.0007345, the number 909, 45.300. This unwieldy number that has zeros all over the place, we're going to figure out what to do with them. And then this whole number, which is 9,106,300. We could even put some commas here to kind of help you keep these numbers straight. So how many significant figures are in each one of these numbers? This is a common exercise you see when students start learning the idea of significant figures. So if we apply one rule at a time here, we see that rule 1, that this 6 is significant because it's a non-zero. But then we have all these trailing zeros. So are any of these significant? Well, we look at because of rule 4, there's no decimal place here. We assume that these are not significant, and so this is one significant figure in this number. So what's going to happen to all these zeros? This will be for our next video. We're going to analyze each one of these numbers, and you'll see why certain things are significant or not. Here, B, we have rule 5 tells us that leading zeros are not significant. So these non-zeros are significant, so we have 4 significant figures here. We have 3 digits here. Are they significant? Well, the 9s certainly are because of rule 1, and rule 2 tells us that zeros between non-zeros are significant. So this is a number that has 3 significant figures. Now we come on to D. So we have a 4, 5, and 3. We assume because of Rule 1 that these are all significant. But what about these trailing zeros? Well, they're after a decimal place. We assume that this is an actual reported value, that fractional value really reflects equipment that could measure to that 10,000th of a unit, whether that was mass, whether that was volume, whether that was time. If we are assuming that this is a truly measured volume, measured from real equipment, real observation, then yes, we can say that these are significant, and we have here 5 significant figures. Over here, we have, once again, a lot of decimal places going on here. We can get rid of this leading zero. I'll show you how we can get rid of it in the next video. And that is not significant, but the zeros between non-zeros, that is Rule 2, that's significant. Trailing zeros after a decimal place, that is significant, so we have 7 significant figures. And then here we just simply have a whole number, there's no decimal place. We assume that these 2 trailing zeros, rule number 4, make this as having 5 significant figures. So hold on, the next video is going to show us what's the relevance of this. Why is it that some zeros will count and some zeros will not count? So what will help us understand at least a little bit more about this is how the idea of significant figures play into the role of scientific notation. And by applying this to scientific notation, it starts making a little more sense about why, particularly in these 2 numbers, more than any of the others, we can really chop out some zeros, because in scientific notation, we can easily get rid of them. Let's move on to the next video and show how that works.